Hello everybody. In this video I want to talk to you about gradient. Gradient is a very important concept in multivariable calculus. So let's take a look. Let me get out of the way here. Okay, so what we're seeing is we're seeing the graph of a function of two variables here. Okay, so that's what this blue surface represents. It's a graph of a function of two variables. And by the way, that function is written right here. It's 1/2 x squared minus y squared. Let me spin that around a little bit so you can get a clear picture of what that graph looks like. Okay, so what gradient represents is it represents a vector that points in the steepest uphill direction. Now the symbol we use to denote gradient is this upside down triangle. And gradient, we apply it to a function to get a new function. Okay, so our function was this one, 1/2 x squared minus y squared. If I apply the gradient to that function, this is called the gradient of f, or sometimes people just say grad f, I'm getting a new function. And that new function gives me a vector. For every point xy, I'm getting a vector as an output. So whereas the function gives me a number as an output, grad f returns a vector as an output. And as I said, that vector points in the steepest uphill direction. But that's just a vague description of what it is. We can describe it a little bit more precisely. If I choose a point in the xy plane, and that's what you're seeing over here. This is the x and y plane. This is that red surface that you're seeing in the 3D picture. If I choose a point here, you'll see that associated with that point is this blue vector in the xy plane. So that blue vector is the gradient. This is the gradient vector right here. Okay, so for every point xy, I get a two-dimensional vector, a vector in the xy plane. Now, that vector, as I said, is always pointing uphill. It's always pointing in the steepest uphill direction. And we can see that if we go look in the three-dimensional picture. So that vector is pointing in the direction that I would want to hike on this graph, if I imagine myself hiking on this graph, so that I would climb the hill in the quickest possible way possible. I'm going in the steepest direction. Now, you'll also see we have sketched these red curves. These red curves are level curves. These are curves of constant altitude on the graph. Now, they are not plotted on the graph. They're plotted in the xy plane. But what you can imagine is if I pushed it down to where the graph was, it would live on the graph and it would be a curve of constant z value. So where the function fxy equals a constant. So solving that equation, fxy equals a constant, gives you a curve in the xy plane. And that's what this red curve is. And one important thing that you'll notice here is that the gradient vector is always perpendicular to the level curve, that red curve. No matter where I put this, no matter what point I choose, you'll notice that the gradient vector is always orthogonal, perpendicular to those level curves. And if you think about it, that should make sense, because if I want to hike uphill the steepest, I probably want to hike in a direction that is perpendicular to the direction that would keep me on the same altitude, right? And that's what that red curve represents. It represents staying in the same height. Well, I want to go orthogonal to that to increase the height the fastest. So that's what that gradient vector represents. It's a vector that is perpendicular to the level curves. It also points in the steepest direction uphill. Let's plug in some other functions and see what this looks like. Let's change this function around a little bit. Instead of looking at 1/2 x squared minus y squared, let's look at 1/2 x squared plus y squared. In this particular case, the graph is of a paraboloid. And if I look in the xy plane over here, to go uphill just means I walk away from that bottom point there. So the gradient vector is always pointing away from the origin. So we see that. And actually, notice that the length of the gradient vector grows. Notice the blue vector is getting bigger as I go to steeper parts of the curve. So not only is the gradient vector pointing in the uphill direction, the magnitude of the gradient vector has something to do with how steep the curve actually is. Let's reverse this. Let's put a negative sign. So now it's a hill instead of a ditch that we had before. So now the gradient vector is always pointing towards the origin, right? Because to go uphill means to walk towards the origin. And in fact, it's always pointing directly into the origin there in this particular case. Right? Let's make one other change. Let's just get rid of the y squared. Let's take a look at this. So here I have just a parabolic cylinder, just a parabola stretched out in one direction. You can see it there. And so the level curves, the curves of constant altitude, are just curves that go along the direction in which the paraboloid, the parabolic cylinder, is stretched out. And of course, the uphill direction will just be orthogonal to those, so it's just pointing towards the y-axis, because the y-axis is the curve at which we're at the highest altitude, right? So you can see that gradient vector is always pointing in that uphill direction. All right, so let's take a look at computing the gradient. How do we compute this? Well, the gradient is computed as follows. The gradient of a function is just the vector comprised of the partial derivatives of the function. So in the x direction, it's the x partial derivative, and in the y direction, it's the y partial derivative. Now we're doing this at a point, right? So the gradient of a function is a function, so you evaluate it at a point to get that vector. All right, so let's do it to this vector, this function right here. This is the first function we looked at, the hyperbolic paraboloid. So let's compute the gradient function. So I'm going to take the gradient of f, and I'm going to evaluate it at any point x, y. Okay, so we need to compute the x derivative of this function. Okay, so if I compute the x derivative, the 2 comes down, cancels with 1/2, so I just get x. All right. Now, what if I do the y derivative of this function? Well, I get minus y. So the gradient of the function is this vector function. Notice that this is a vector that depends on my coordinates x, y. If I wanted to know what the gradient of my function was at, say, the point 1, -2, well, I would just plug in 1, -2 for the x and the y here. And we would get this vector. Let's take a look at what this would be in that three-dimensional picture. Okay, so let's see if I can find 1, -2. So that would be right about here. All right, so we're looking at this vector. Now remember, we computed the gradient. We said it was the vector 1, 2, and so that makes sense. That's what we're seeing here. That's what this blue vector is. In the picture, let's see where we are. We are right here, right? So we're at the point 1, -2, and the vector's pointing us this direction. What it's saying is that on the graph, that is the direction that you would want to move to go uphill the fastest.